All right. Is it? All right. So let me get started. So I am Mudhakar Srivatsa. I am from the IBM TJ Watson Research Center. So I'm going to be talking about trouble ticket routing in call centers. I'll sort of explain what the problem means in the next few charts. But there are a lot of people behind the scenes who we have collaborated with when we were doing this work. Folks from, of course, other colleagues of mine from IBM, Daria from Surdek, Nosh, of course, all of you know, colleagues from UCSP like Shifeng, and folks from Army Research Lab, Sue Case and Michelle Vani. And obligatory acknowledgement to the Network Science CTA program for continued funding and helping us do all this work. All right, so what is the problem that we are looking at? We are looking at the problem of expert networks. So we have a collection of experts that are connected in some manner, and they are trying to collaboratively solve a particular problem. So what happens here is that when one expert is not able to solve the problem, they will route the query or the problem to somebody else who might in principle be more capable of solving that problem. And there are several such examples that we can provide. Examples range from consulting, troubleshooting services, and one such example is like a call center where it could either be a voice based call center or could be web based. You know, I have a problem, I submit a description of the problem in text, and the problem gets routed on this expert network, or it's a call center where I actually pick up the phone, call somebody, and it bounces off. We all have had our share of bad experiences with the call center, I'm sure. But this is an effort to sort of deconstruct and understand what is actually happening behind the scenes. What, if any, can we do with network theory to better understand the problem, and how can we improve it? There is, of course, a lot of work, say, from Nosh and his team on how we can bring in agent-based simulations into the picture. So this talk is going to be actually a combination of data mining, where we are looking at data set that we obtained from a real world call center. We are analyzing it to see how people make their decisions on routing a particular problem. It has a combination of network theory, where we look at the fundamental structure of the network and try to determine how well this particular network can perform. And we do have a factor coming in from agent-based simulations to sort of validate what we can do beyond just the data sets themselves. So the problem is very simple. Sort of a query or a problem comes. Question is where to send it if I cannot solve the problem. And typically the question you ask is, what is the sort of the quickest way to solve the problem? So of course, just to clarify, I mean, let's say the person receiving the query is Sophie. I mean, if she already knows, if she has full knowledge of the network, if she has in some sense an idea as to who can solve the problem, then it degenerates to a simple shortest path routing query, because I have the full network structure. I know which set of people can solve the problem, so it just becomes a shortest path routing problem. But in most real networks, Sophie only has a limited number of contacts. So for instance, she might only know about her immediate neighbors and not really about people who are further away on the expert network. So given this limited knowledge, the question that we ask is, which of her contacts may solve the query, and which of the contacts of her contacts may solve the query, because again, we do not know if the query will get resolved in a single hop. More often than not, it does not, and I am going to show you sample data where expected number of hops is around 3.18 to answer these queries. Anywhere between 2 to 5 is quite normal to be expected here. So what are the problems that we are trying to address here? So first is, like I said, a data mining approach, where we looked at data from a particular call center, and we are trying to determine what is the thought process in an expert. I mean, can we model the expert using a generative process and say that this is how the expert is routing the query? The second question we are addressing is, given a structural property of the network, for example, lot of these networks can be modeled as a power law graph. So given the power law exponent, can I say, is there a phase transition that happens? I mean, is there a value of R below which the network is efficient, and I'll define what is efficient in the subsequent charts, and a threshold when you pass, the network suddenly becomes inefficient. And it just so happens that in these networks there exists such a phase change that happens. The problem solving remains polylog for certain values of r, and you go beyond a threshold, suddenly it's no longer polylog. Then the question becomes, so of course in the first two cases we are basically addressing the problem of one expert being able to answer the query, which again is not realistic in several settings. Sometimes you need a group of people to come and solve the problem. So the question really becomes, how do we assemble a team to answer a more complicated query, that which a single person cannot solve? And this is where a lot of work on agent based simulations come into picture to sort of help us solve this problem. Then there is again a very interesting question. This is a question that, say, all human resource department wants to know is answer to this question. They don't really care about the network theory. They just want to know, who do we retrain? I have a limited budget. I have $100,000 for retraining. Find me people from the network that whom, if I selectively invest money and retrain, I get a biggest bang for my buck. So how do I identify these set of people? And the fact to be kept in mind here is that when we are enriching the knowledge of a person, we are implicitly enriching the knowledge of their contacts and contacts. So when we pick people, it's not necessarily based on the person's capability, but we should also look into the network effect of educating that particular person. All right, so these are broadly the 4 problems. Again, depending upon time, I may not cover all 4, and we will see how far we can go. And do feel free to interrupt me to ask any questions. And again, for full disclosure, I mean, generally I make this presentation to computer science audience, so it's going to be interesting to make this presentation here. I am expecting some oddball questions, or curveball questions, that which I'm not used to. So it's going to be a good exercise. All right, so let's start with the first of the 4 problems. So expert routing behaviors. So what we do is, we have a data set, we can look at how people are routing. First observation, almost trivial, people do route to different set of people. So it's not like a person is always going to send it to one given particular contact of his or her. The question really is, are they picking the contact at random? So maybe I have 3 friends, do I at random pick one of these 3 friends, or do I make an educated guess as to which particular neighbor of mine is better suited at solving the query? Yes.
How are the incentives set up in the call centers that you're getting your data from? If I don't know the answer and I send the query to Peter, and Peter answers it, does he get a bonus? Does he get extra recognition? Do I lose some recognition when I forward a lot of queries? So would there be an incentive for me to just forward everything because I don't want to do my job?
No.
How are those balanced?
So it is a combination of 2 things. One is when the overall query gets resolved, the person who actually answers the problem gets credit. The people who routed get credit for reducing the overall time to answer the query. So there are 2 types of credits that gets associated. And in fact, what I am told is that they do train people who are good routers, and they do train people who are good problem solvers. And the fact is that they need both kind of people. So I cannot comment as to what is the relative incentive between those 2 classes, but both are incentivized. I mean, when you have a typical network size here is maybe like about a few hundreds of people. So you do need people who don't know the answer to the problem, but they know who might have the answer to the problem.
Have you or they observed any kind of collusion that Peter will say, hey, that if you forward these queries to me instead of to Michael, I will split the bonus that I get for answering them with you? So
Good.
How far does strategizing in those networks go?
I don't know how strategic they are. In fact, yeah.
I'm not saying that might affect.
Oh, definitely.
Their choice of what
Definitely. Those things would very much affect, because ultimately all these things do translate into actual pay raises and bonuses and so on. So very much.
That's how a game theorist would think about
Yes.
design problem.
Yes.
You mentioned there's a lot of churn in these networks, so maybe that counteracts that.
So there is typically like a 10% a year churn in these networks. I mean, if you look at a lot of large corporations, maybe the overall churn may be actually under 1%, 2%. But in this particular class of jobs, there is higher churn, generally speaking. All right, so yes, so there is the game theoretic effect, which we have not looked into in this particular problem. So the question that we are trying to address is what sort of a strategy might somebody be using to forward the query. And the second observation that's probably a little bit more interesting is that who do I forward it to? So if we model the expertise of an individual as a vector using any sort of latent semantic modeling, how far is the expert to whom I am forwarding the query to in terms of the distance between the two expertise vectors? What you find is sort of a distribution where the expert tends to transfer a particular task to somebody whose expertise is neither too far away nor too close to my own expertise. Too close is probably easy to explain. What is the point if I forward it to my friend who knows exactly what I know? Too far away is probably because of the way the social network gets constructed. I mean, I probably do not know enough people in a completely different area of work to whom I might be able to forward the query to. So it has this sort of log normal distribution kind of a shape where there is a certain sweet spot of expertise difference where most of the queries get forwarded to. Yes?
So is there any like a hierarchy between experts?
Yes, so there is a 4-level hierarchy, level 0 to 3 as they call it here. Level 0 are typically entry level experts, and as you do imagine, there are more level 0 people in the network than level 1, than level 2 and so on. Yes.
And can they reach anyone in those levels? So for example, can a level 0 reach a level 3?
So we don't generally allow that. I mean, there is nothing that prevents it from happening. That's what we are told, and but we don't find a single instance of that happening in several months of data that we have looked into. In theory, or the system, for example, the forwarding system does not prevent you from forwarding it to a skip level, but in practice it seems it does not happen. So the assumption, so let's look at the problem as follows. First, I determine which pool of people might be able to answer the query, and then pick a particular expert in my immediate neighborhood to ask the query. And what we are looking at here is a very simple generative model. So first is basically a task neutral routing where I sort of randomly pick one of the neighbors, and second is more of a task specific routing. And we use a very simple logistic model for doing task specific routing. So we modeled the expertise of the user as the expertise vector EI. We modeled a ticket as again a vector T, and we use a logistic model to sort of determine what is the probability that this particular ticket T, I send it to my neighbor EI, for instance. We look at again various very simple models, one where I do uniform and random selection of my neighbors, one where I do volumetric based on historically I observe that the number of the probability of EI transferring the ticket to EJ is just proportional to what we have seen in the past, for instance. And the last one, of course, being the expertise difference, which we approximate this empirical distribution using a log normal distribution, and then we draw from this distribution to determine the probability of transferring the ticket, for instance. Now, what we do is that we model every user as a linear combination of 6 different routing patterns. So you have the random routing, you have the task sensitive routing, and you have uniform random neighbor selection volume based and expertise based. So you model it as a combination. So somebody probabilistically picks one of the 6 routing patterns, and as an expert, your vector, which is of size 6, determines how you are picking the probabilities. For instance, one expert could be all zeros except a 1 here, meaning I almost always do only expertise difference based routing, for instance. And some other expert could be just random routing, so a 1 there and a 0 everywhere else, and in general people could be anywhere in this particular spectrum. And what we are trying to understand is that what is the spectrum in this particular group of experts that we observe. So I am not going to get into how we are doing the generative process modeling, it is fairly simple. So we do that, and the goal here is to understand what fraction of the people are doing, say, task-specific routing versus random routing. Are there any advantages of one over the other, for instance? To do that, we are looking at 3 particular data sets. The name of the data sets itself might be irrelevant, but some of you might recognize that this is a database, this is a web server application, this is an operating system. And you have about so many tasks. These are all trouble tickets that arrive in the order of few tens of thousands. And this is the size of the expertise network that addresses this particular problem. And this is the percentage of tasks with a completion time, but in this case completion time I am just representing it in terms of number of hops. So we do have the real valued representation of the completion time as well. So number of hops equal to 2, 3 and greater than or equal to 4. So just to give you an idea as to what the data set looks like, and like I said, in most of these cases the average number of hops is somewhere around 3.2 or so. Yes.
What's the rationale to measure completion time in terms of hops as opposed to actual time of completion?
Okay, there is the only reason is that I am not allowed to give you the actual completion times in minutes or hours. So
You don't want to make IBM look bad.
I don't know. The numbers actually look pretty good. They should be actually be proud of it. I don't know why they don't do that, but there is beyond that there is literally no other reason why that's the case.
I asked just because you could imagine that maybe multiple hops is actually quite efficient.
Could be.
You know, if you find a high correlation between hops and time to close a ticket.
Yes, very high correlation. In fact, we do have our analysis on the actual completion times as well, which I'm not going to be talking about here, just because we are not allowed to, but yes.
Why is there no one hop? Is that the definition thing that one hop would be just the person posing the query, or is the first level always someone who has to route?
First level is always, level 0 is only for people who are routing. Yeah. Very good point, yes. That's the reason why you'll never find equal to 1. Alright, so the generative model works fairly well. I mean, we do have a comparison with several other baseline approaches, and we just use a simple prediction time, the error in the prediction time, to sort of estimate how far away we might be from predicting the actual completion time. More than that, that's not really the point. I mean, of course, these other models did not consider sort of a generative process with different sort of routing strategies built into it, which was accounted for explicitly. But more important to understanding the network was to see what fraction of people are adopting a task-specific routing versus random routing. Are the people who adopt task-specific routing sort of clustered together? Is there a correlation between the level, because we said there are 4 levels, and whether people are doing task-specific routing or task-neutral routing? Those are all some of the interesting questions that were answered in this process. So just a quick summary of where we are. I mean, at this stage, what we have done is we have taken a data set, use a data mining approach to figure out what sort of routing strategy is implicitly happening by an expert, and we understand a distribution of these routing strategies over a pool of experts. Now we are looking into the question of performance bounds and guarantees. Is there something fundamental about the network structure that which has a bearing on the network performance? By network performance, I mean completion time of a query, again in terms of number of hops, but not in terms of absolute completion time. Alright, so we are going to sort of bank upon this sort of a distribution that we are seeing, and since we have measured it over, actually I have shown 3, but we have measured it over 9 different data sets, we can fit in a log normal distribution fairly well across these 9 different data sets. So this seems to be sort of something that's little bit more universal about how expert network might be routing a query, wherein it's neither too close in expertise nor too far away in expertise. Now what we are asking ourselves, the question is, can we model it using network theory? And we are adopting a very simple model. So homophily means, of course, experts connect to experts with similar expertise. Heterophily means each expert also connects to a few much smaller number of experts, but with highly dissimilar expertise, for instance. So this results in a sort of a generic network model using which we want to sort of determine the following things. Can we come up with performance bounds, and again under what conditions does the network perform well or not. Now, to do this, let me just set up the problem in extremely simple terminology so that we can all follow along. So, let us say that an expertise W is associated with a vector, expertise vector say EW, and all the things in the vector are all positive. A query is a tuple, again it is a vector, I being the problem area and tau being the difficulty in that problem area. So, we have a semantic representation, latent semantic representation of the expert's expertise and the trouble ticket in the same semantic space. And the way we say that a query is solvable is extremely simple. We just say that the expertise vector dominates the tickets vector in every single dimension of the ticket, for instance. So, the routing strategy is extremely simple. All that we are doing is that from our whether we are first checking whether we can solve whether I can solve the query or not, and if I cannot solve the query, I find the expert that is best capable of answering that particular query. So, it is a very simple decentralized routing strategy. Simplicity actually helps us in sort of analyzing it very rigorously and understanding how well the network works. So, purely based on local knowledge people route. So, all that I mean is that an expert knows the problem solving abilities of only their local and long range contacts. Like I said, the network has homophily, people with similar expertise. Long range contacts is heterophily, people with dissimilar expertise, but those whom I have direct contact with. What they do not know the expertise of any other experts other than my long range and short range contacts. And if they cannot solve the problem, they do not know who really can solve the problem. Yes?
Can you tell us if the experts have unique knowledge, or do they have overlapping knowledge?
Almost definitely they have overlapping knowledge. Almost definitely, yeah.
So there's the necessity to distinguish between them so they can find them.
Yes, yes. So, let me first start off with a very simple what might look like a force fit, and then I will sort of remove these constraints, right. So, let us embed all the experts in a two-dimensional grid. So, let us say this is me, these are my immediate short range contacts, my local neighbors, and what I do is that you might have a link direct contact with W, but what I do is that the probability of that link is distance between U and W, and in this case distance between U and W is 5 hops away. So, distance raised to the power of minus r, where r is some parameter of the network. So, as you can see, r of course has a direct relationship with the power law characteristics of the network, where we are saying that we embed experts in a two-dimensional grid. Short range contacts they have, but long range contacts they have with a probability which is inversely proportional to distance power r, for instance. So, for example, here U and W have a distance of 5. So, the probability that U has a direct connection to W is something proportional to 5 raised to minus r, for instance. All right. So, here is what we can show. Again, it is an overly simplified model. We have, for the sake of convenience, embedded all the experts in this two-dimensional grid. We are making assumptions on short range and long range contacts, but we can see a clear phase transition here, and let me explain this in a few minutes. When r is in a particular range, say between 0 and 1, if I sort of ignore some of these other terms, the key term I want to focus upon is this term. So, the complexity of routing or the amount of hops it takes is polynomial in the logarithm of the size of the network. So, meaning if say the network has 1,000 people, log of 1,000 to the base 2 is say 10. So, it is polynomial in 10 as against something being linear in the size of the network. So, for example, when r is greater than 1, and as you note, this big O is an upper bound that we can show, that when r is within this range, we can bound the expected time to route a query using the simple decentralized routing model in polynomial of log n. When r is greater than 1, this sigma refers to a lower bound. So, we in expectation the cost of routing is n power r minus 1. So, here you see the difference between log n and n. So, suddenly what was extremely efficient, something that used to take say roughly log n square, say r is 1, log n square when r is equal to 1, it suddenly jumps all the way to n power something. So, from logarithm of n, you say you go to n power square root of n or n power 2 by 3 and so on. So, you basically observe this phase shift that happens, and you can actually mathematically prove that when R is operating in this particular region, it is efficient, and when R is operating in a greater than 1, it is in fact inefficient. Sadly, it just so turns out that almost all our networks operate in this regime, but nonetheless we sort of get an understanding as to what makes it efficient or less efficient. There are other network models I did not talk about. One where we have experts that are whose total expertise is roughly a constant. So, again, if you look at the way I have structured the expertise, let us say 2 dimensions, if you add up the expertise in both the dimensions, it is a constant for every single expert. In this particular model, experts have heterogeneous expertise. So, meaning if I add up the vector, the entities of the vector, they do not add up to a constant. But in this case, again if you ignore all the constant terms, you will find the same sort of a relationship, log n power a constant. So, it is polynomial in log n, versus here it is lower bounded by n power something. So, there seems to be this very inherent characteristic of R, meaning R, as you know, is the probability for my long range contacts is d power minus R is the probability, and that has a very tight relationship with whether routing is efficient or not. So, with this, let me start relaxing the model. I mean, I know this particular model looks a little bit artificial. I have forced all the experts to nicely fit a grid, and I am saying that there is a certain probability of long range and short range contacts. But again, the beauty of some of these network science like programs is that we get to talk to people like Noshir, who can give us some feedback on this. Does sound a little bit contrived, it is a convenience to get some nice theoretical results, but can we relax this, make it more intuitive and yet provide strong guarantees, and it so turns out that we can. And let me give you sort of again at a very high level explanation of our more generic network model. So, the idea comes from group complexes. So, each expert is a size of one group. So, an expert is a degenerate group by himself, and the group size is 1. The total network itself is a group G, and we sort of have this constraint, and let me first read this constraint and sort of explain it to you. So, for all groups containing a common expert U with group size lesser than a threshold, the union of all these groups is bounded by a constant factor of that. What it means is that, say if I have a group of size n, right, and if I look at the union of all these groups to whom I belong to, it is bound by a small constant, meaning if I belong in 2 groups, it is not like the 2 groups are completely disjoint. If they are completely disjoint, and the more the number of groups I belong to, the union of all those groups will grow unbounded. On the other hand, say I could belong to 100 groups, but the union of all those 100 groups, the size of it is still bounded by a particular threshold beta. So, it is not unbounded, it is not 100 times n, for instance. So, this just goes back to a typical assumption that people make in sort of social network cohesiveness. I could belong to multiple groups, but it is almost not the case that these groups are completely disjoint. These groups have certain cohesiveness. So, if I take the union of the size of all the groups, there is still bounded by, say, a factor beta, which is a constant factor multiplied by the size of the group. So, this sort of gives us a little bit more intuitive way of explaining how groups are constructed, as opposed to sort of a model which force fits experts into a grid and says there is a certain probability of a long range connection. Now, let me define how this works. So, let us say SUW is the smallest group containing both U and W. The beauty of how the underlying math works is that what I was earlier calling as D, the distance between 2 experts, I could replace it with SUW. It is the smallest group, that size of the group that contains both U and W. Everything else remains the same. I just replace D with SUW, and the minus R, the exponent minus R, and everything else remains the same. This is just a more intuitive way of constructing the expert network than force fitting it into a grid. And it so happens that almost every result that I talked about in the earlier chart works when I make this assumption. So in some sense, it's a more generalized model. In fact, if you apply this model to exactly the grid structure, you will get back everything that I talked about, but this is a more generalized model. So I'm not going to read again the whole thing, but the point being that when r is between 0 and 1, I still get back my polynomial in log n. And when r is greater than 1, I still get a lower bound, which is n power something. So it is still very inefficient when r is greater than 1. So what this lets us do is that we sort of go to a more general network model, and we are able to argue how well or how poorly the network performs. And it just still so happens that this magic value of r equal to 1 exists. So below 1 it is efficient, and suddenly it becomes inefficient. The phase transition happens at r equal to 1. All right, so let me skip a couple of these charts and go to something that might be more interesting to this one, where this is the case study that we ran with respect to our own call center. We had a couple of data sets that we were working with, and let me directly go to these results, right. So this is slightly different data set from what I used earlier for data mining, but nonetheless the characteristics remain the same. So we have two different operating systems, we have a database and we have a web server. So these are 4 different expert networks that we studied. N is of course the size of each of these expert networks. So R1 was the empirically estimated R parameter, meaning how many local contacts I have, how many long range contacts I have. So I empirically estimate what is the exponent in this power law distribution. And this was the estimate as of January 1st of 2015. So we made these estimates as of January 1st. So of course the theory suggests that when r is greater than 1, you are likely to have less efficient routing. So what happened was we could convince the team to have what is known as a mentorship program. So in this mentorship program, it was a pair mentorship program. So there were pairs of people, typically person with limited expertise and knowledge is paired with somebody who's a lot more experienced. The idea is to induce a long range contact, because more long range contacts occur, r value is going to decrease, and the theory suggests that lower values of r is definitely better. So over a 6-month time period, this pair mentorship program was run. It was typically run in the form of, say, lunch coupons, incentivizing people, the pair to sit together, have lunch, incentivizing people of that kind. I mean, it's not really per se signing up somebody to go attend a class or get trained in a particular field, but this was more like trying to get 2 people together so that they can have this conversation and sort of build this contact between somebody whose expertise vector is small with somebody whose expertise vector is relatively much different from me. So after the 6-month program, we again collected 3 more months of data, and these were the values of r after intervention. Basically the mentorship program was run, and it just so happened that there was a clear drop in the value of r. So presumably whatever they did for mentorship, the pair-wise mentorship, seemed to work. Now, if we go by the sort of the theory and we try to estimate based on the value of r and only r, and granted that there are so many hidden variables here that we do not have control over, like for example, like I said, this is of January, there was a 3-month January to March data set from where R1 comes from. There was a 6-month mentorship program, and this was from September to December data. And granted, in this time there are a lot of people joining, leaving, things that we cannot control for. If we look at the real improvement in performance, so this is basically L1 is basically the expected time to complete a query in R1, basically in the January data set. L2 was the expected time to complete the query in the September data set. So these are from real measurements, and this is what the theory would predict as to how much it should have improved because we were able to decrease the value of R, for instance. Again, it's not a perfect match. I'm not going to even try giving any sort of statistical confidence measures on this because I cannot. But the point here is that it was useful in sort of being able to objectively go to a team, convince them that here is hard theory, there is something special about this R, which is, and we have evaluated it empirically on so many data sets. You really have to try and decrease this value of R. You have to incentivize long range contacts. So as a result, the intervention was done, and seemingly there was significant improvement when the intervention was done. And like I said, even after the intervention and all the theory says R lesser than 1 is better, we still cannot get to R lesser than 1. We need to figure out, is there something intrinsic about the way people work that maybe it's just too much overhead to have R lesser than 1. There might be some fundamental cognitive limitation to having a very small value of R. Small value of R means more long range contacts, and they might be more taxing to a person than, me maintaining a relationship with people who are similar to me is probably far less taxing to me versus me maintaining a relationship with people who are somewhat dissimilar from me presumably is a lot more taxing. So while of course the theory can say anything, R lesser than 1 is better, but maybe there is a certain cognitive limitation to achieving R lesser than 1. All right, so that's basically one portion of this particular talk, where what we have done so far is to first use a data mining approach to understand how experts route a trouble ticket. Then looked at network theory, can we model the network in some form, identify phase transitions where it's efficient, inefficient, and so on. And all that I'm saying is that these results provide guidance on how we can plan for more complex expert networks. So with that, I'll sort of switch gears a little bit and start talking about team assembly for complicated queries. So we look at team assembly also as a routing problem, and I'll sort of explain how that works. So the way it works is that instead of in the earlier case, the problem goes to one person, the one person determines who to send it to. In this particular model, the problem goes to a team. So say it goes to two people. When the team cannot solve the problem, the team picks somebody from its immediate neighborhood. Let's say the problem goes to me and Nash. If say we cannot solve the problem, I might decide to substitute myself with say Ambuj or somebody else, for instance, right? So the team size remains the same. So like earlier, the ticket was only with one person at any given point in time. Here the ticket is with a fixed set, maybe two people or fixed set of three people. The option that I provide is that if the current team cannot solve from their immediate neighborhood, they can pick somebody else to substitute themselves. So I could decide to substitute myself with somebody else, and that becomes the new team that tries to go and solve the particular problem. So so that's basically the way we are modeling this as a routing problem. Here again, we are assuming local knowledge. So we do not assume that I know the expertise of everybody in the network and identify the team. The problem goes to a particular team, and the team has its immediate neighborhood within whom they can rejuggle the team, and the problem can get routed, quote unquote, in that particular manner. Question again is the same question: what is the routing efficiency in relationship with the network properties? All right, so just a few minor differences, but perhaps, but let me just quickly state it. So the difference here is that we have a probability of local contact and a probability of long range contacts. Something that I might have forgotten to mention is that in the earlier piece of work, short range contacts was not probabilistic. There were a certain minimum number of short range contacts. In this case, it could, because it's probabilistically drawn, the number of local contacts could technically even be 0. While in the previous work, the math does not work in that manner. We need a certain minimum number of long range contacts. Just a small technical difference, but something I should clarify. So again, the routing strategy is again decentralized, and the routing works by expanding on the team. Expanding meaning by substituting myself with somebody else, for instance. All right. So again, very simple models. One is just I know the expertise of my immediate neighborhood, 2-hop neighborhood, and global knowledge, just for a baseline purposes, right? So what we did was we tried to look at through agent-based simulation models. So on these things, we are still trying to figure out if we can mathematically establish the same kind of bounds that we established in the other one. But we are not there on the team-based routing. So we worked quite closely with Nosh and the student. I mean, we have, maybe I should take a minute to advertise for our summer internship program. We do have a very large summer internship program, and we always look for strong students who can come spend 3 months or so with us in the summer. And I can assure you, New York is very beautiful in the summer. So, okay, back to the presentation. So, Nosh student in fact came and spent 3 months with us, where he helped us with a lot of this agent-based modeling simulations. And we were trying to figure out with these simulations, what is the mean length for team assembly using a search process, basically the way I described earlier. And what we observe here is that when we do familiarization based forwarding versus when we rely upon the different strategies, local contacts, 2-hop neighborhood, and the global contacts, the sort of the mean time it takes for team assembly is going to vary. And local contact search strategy consistently shows good performance, but the failure rate is very high. So while the mean path lengths look good, if we look at the failure rate of failing to construct a suitable team is very high. And again, by simulations, we see that this R seems to matter, because when I set R greater than 1, here again the successful rate of team formation drastically drops. But again, we need to sort of work out the math to see if indeed the phase change results apply here as well. So that's basically here. I mean, I'm told that sort of the 45 minutes time is roughly over, so I'll pause here and I'll open it up to questions.
Question?
Yes.
So when you look at this, the multiple expert, the multiple team routing, what is the model for who answers the query? Is it still a single expert, or is it multiple experts that come together to answer?
It's a team, so it's a team. And what, again, if you go back to the oversimplified models that we have, we just say that an expert can answer a particular query if the expert's vector dominates the ticket vector. Now, in the case of a team, it just means that there exists an expert which dominates the ticket in the ith coordinate of the vector. So I know it's an oversimplified model, but
so,
yes.
So you need to find one expert that is going to dominate the entire.
No. I could dominate on, let's say there are 2 components, x and y. I dominate on x, you dominate on y, which means the 2 of us is a good team to solve the problem. I know it's again very simplistic model. I mean, I don't think that teams are additive in that manner, and that's, I mean, these are the limitations when we, when we initially want to build a mathematical model. Of course, we sometimes go in for this very simple models, but hopefully, just like we fixed some of the limitations, we hope to fix more talking to people like you here. So. Yes.
So it seems like your model bears a lot of similarity with the Kleinberg small world routing model.
Yes.
And but your result is different in the small r range. So
Yes.
for Kleinberg, I think r equals 1 is the unique exponent.
Yes.
Where things work, and for you it's r less than or equal 1.
Yes.
What is the quantitative difference that makes that happen?
Exactly. In fact, I had a chart, but I skipped it. But so Kleinberg's work shows for r equal to 1 it's efficient, and that's because it's point-to-point routing. We are looking at any cast routing, meaning any expert who can solve this particular problem. In Kleinberg's case, it's I need to send a message to Nosh. The only person who should be receiving that query is Nosh. Nobody else can handle that particular query. That's the difference. So here we do have more people who can solve the query. There is not a single person. So in networking terminology, it becomes from a unicast problem, it becomes an anycast problem. But that's the reason why you get a range of R's for which it's efficient. Yes.
And so follow up in the Kleinberg result, while in the limit as the network size goes to infinity, R equals 1 is the right exponent.
Yes.
I think all the simulations show that as n is relatively small, it's like some 1 plus epsilon that depends on n. So does that also carry over? And so maybe going all the way down to 1 or below for finite n, in particular for n equals 100 or 300 in your case, maybe the right exponent is actually 1.2. Or did you sort of try to evaluate that precisely, or did you just look at the asymptotics?
We did, so in the data sets, of course, we cannot control the value of R, but through simulations and agent-based simulations, we are able to do it. And the range still holds, it's not 1 plus epsilon. I mean, in several cases, we find that at 1 plus epsilon, it is still efficient. But definitely when epsilon becomes, say, even 1.1, 1.2, you can clearly see the departure. I mean, the curve no longer looks like polylog. It definitely, you can see the knee effect and it's taking off.
Even for n equals 200?
Yeah, even for n equal to 100. Yeah, we do see that, yes.
Still a few minutes. Is there anything you want to add to your presentation?
I mean, I don't think I have enough time to add, but yes.
Yeah. How do you intervene? Suppose, so you're saying that the system is not being efficient. Have you thought about what would you do to intervene? Whether you would add more experts, or you add a different network structure. I mean, you have two ways of trying to.
Correct.
You can either add new nodes, or you can add edges.
So in this particular case, it was adding new edges, right? In this particular intervention that was done, the pairwise mentoring model that was introduced, what in effect it induces in the network is a connection between me and somebody who has a dissimilar expertise vector than me. So it induces a long range contact, as the way we call it. So it's basically inducing new links in your network, because of which this R exponent goes down, and we have results from before and after this particular intervention was done. We do have a second thing which I don't think I have enough time to cover it. So here we are asking the question, which set of experts I need to select for retraining, meaning these set of experts I select, I have a finite budget on how many experts I can retrain, and I focus my efforts on a small number of experts for retraining. And the effect we are trying to capture is the network effect. I mean, because I am retrained, I do have a certain social influence, and definitely my immediate neighborhood gets the benefit of retraining me. So when we are picking somebody for retraining, it's not essentially dependent upon just myself, but also my position in the social network. And in fact, when you are picking k nodes for retraining, it depends upon the position of these k nodes in the social network. And what we are trying to do is to maximize the influence or the effect of retraining these set of k people.
So when you retrain, you only affect the edges. You're not affecting the the node vectors.
When I retrain, I am only affecting the node vectors.
Okay, you're affecting the node vectors.
But
how about the edges?
No, there is no affecting the. So the edges was basically the mentorship intervention where we are inducing new edges. Retraining is basically affecting my expertise vector, not my edges. I mean, again, there is no reason why both should not be done concurrently, but yeah, definitely they can be done concurrently.
Can I ask you more? I know Nosh wants to ask you another question.
Sure.
I'll follow up before Nosh. So there is this work on the transactive memory systems. Have you looked at what is effect? I mean, Nosh knows a lot more about this than I do. But what is happening in terms of can you measure the effect of that, whether an efficient transactive memory system has been set up in this framework?
Is that a question for me or for Mudhakar? So, I mean, transaction memory was the impetus for us to start working on this project in the very first place through one of those ARL get-togethers, etc. And in a very primitive way, the model comparing whether you only know about the expertise of your immediate contacts versus whether you also know about the expertise about your contacts is a very simple example of transactive memory. You can say, I only know what but actually, even though Ambuj knows Shifeng and I don't know, the fact that Ambuj knows about him means that I now know more about Shifeng's expertise through Ambuj, for example, right? So that's, and that's why we're using the default model, which transactive memory would not assume, which is you have global knowledge of everyone's expertise. So in a very simple way, that the comparison of those three models is a very simple way of being able to say to what extent is your awareness of either your immediate contacts or your contacts going to be different and affect the routing both in terms of success but also in terms of number of hops as compared to the default assumption that everyone knows about everyone's expertise, which transactive memory tells you is not not necessarily the case.
Thanks.
The follow-up that I very quickly, oh sorry, go ahead please.
No, you can finish.
Go ahead.
So I had a question. So thinking about this problem with getting R less than 1, I was curious if you had any data about the spatial arrangement of the experts, given that they probably will know people who sit near them, and if all the level 0s are next to each other, then they're going to know other level 0s and not level 3s. And so you had a social intervention to build these connections, so maybe you could rearrange seating to...
That's interesting. I actually do not know what is the physical layout of this particular center. No, I don't know. But that's a interesting intervention that could be tried out as well, where we rejuggle the relative positions where they are sitting, and maybe that does help in forming these contacts. So maybe mentorship is not the only way, I suppose. Yes, but that's a very interesting suggestion. Yeah.
Go ahead, not after you.
I was just going to invite you, because you mentioned as you were wrapping up, you said that in the case of the direct contacts, the number of hops were very few, but the success rate was really bad.
Yes.
Can you talk about what happens when, I don't know whether you had a chance to talk about what happens when you are looking at the scenario of not just your direct contacts, but your contacts, and what that does in terms of success rate versus...
So it definitely increases the path length in some ways, but it does significantly improve the success rate. So it's very important to go beyond that. It appears for at least team-based. And we are still figuring out why that is the case. I mean, what is the reason? Because in a lot of cases, local knowledge is very good, right? I mean, all the previous work that I presented here, it was just based on one hop local knowledge. Why is it that here it is not sufficient? I mean, we still are examining it. I mean, is it a curse of dimensionality that we are dealing with in the case of agent-based simulations? Because I need the ticket vector to be dominated on every single dimension by a collection of experts. Is it some sort of a dimensionality curse problem? We are still exploring these issues, and hopefully we'll have the answer soon for that.
So there is a relationship of this work to the earlier presentations by PJ had presented in terms of, so he had this model in terms of the layout based upon what you know.
Yes.
So how would this, could you model it as some kind of a latent space where you have different categories, and just based upon where you are in the latent space, you know your neighbors, and so you don't, so the neighborhood is the result, and who you know is a result of your knowledge.
Yes.
So there was this search problem that PJ mentioned about it, and then Russell's work on the stack exchange data set, where you're looking at these bridges and using that to guide your search.
Oh, yeah.
So, I mean, there's a relationship of what you're talking to, at least I see.
Absolutely. Yeah, I mean, here, like I said earlier, I mean, the network connectivity is, we are modeling it in a generative manner in this, using homophily and heterophily. Homophily just says that I as an expert will have few people with similar expertise as myself in my immediate neighborhood. But I also do have a few people in the heterophily category. So these are experts who have dissimilar expertise than myself, but I do have a few of those contacts. So the underlying model says that farther away the experts are, the less likely I'm going to have a contact with them, because it's inversely proportional to the distance between the two experts raised to this exponent r, negatively raised to the exponent r. Right. So that's the very basic model under which we are operating. So by construction, what it does is that if I set r equal to infinity, it destroys all the bridges, because any long range contact, the probability goes to 0. So I'm not going to ever have a long range contact, meaning I've burnt all bridges in terms of long range contacts. If I set r equal to 0, it means very dense network. I probably have uniform and random connections to everybody in the network, which sort of is infeasible. It just increases the cognitive load on a person to maintain so many contacts, for instance.